get, and from here I'm going to get uyy to be equal to minus 9 by 4 w eta eta plus 2w eta eta plus w eta. Okay, so now original equation was uxx plus x uyy. There is no cross term here, so I don't need to evaluate the expression for uxy. Okay, so I have already found uxx and uyy in terms of w zeta and w eta, etc. So when I plug these expression in, I'm going to get this form. This might go minus zeta raised to 2/3 w eta eta plus w zeta minus w eta 6 zeta minus zeta equal to 0. So you can see this is, since eta is not equal, eta is zeta are not necessarily the same. So this will give me essentially w zeta eta plus terms involving linear derivatives of w with respect to zeta and eta. Okay. The first derivative terms of w, okay, with respect to zeta and eta, that is equal to 0. Okay. So we have only this term, the cross term appearing. Okay. Okay. So right. Okay. So here, although the coefficient of w zeta eta would be negative, so if you have this form, you can see that whatever the coefficient be for w zeta eta, okay, meaning whatever the value of b, the sign of b is, okay, this 2b is always, it can be plus or minus 1, does not matter. When you take square of that, b square minus ac will always be positive because ac is anyway 0 and b is a positive number or negative number. B square will always be positive. B square minus AC is positive. So whatever B square minus AC was, that value, that sign is conserved when I made this change. Okay. All right. So essentially this will be the form of the canonical. This is canonical form of the given equation. The equation that I gave. Okay. First you find out what is the sign of B square minus AC. Then you know that, okay, so I have to have parabolic or elliptic or hyperbolic, etc. And then you reduce that particular equation to a particular canonical form for that kind of equation. So this is having only one mixed derivative or cross derivative term is a characteristic of hyperbolic equation. This is hyperbolic equation. Okay. So you remember x, y equal to constant for hyperbola. So the way to remember is the product is a hyperbola, so it's constant. So that's why I have w zeta eta. It's like x, y is analogous to the zeta eta. So only w zeta eta will appear for hyperbolas. Okay. So that is okay. Now parabolic. Okay. So let's see parabolic. Elliptic. Let's see. We'll have probably. We will discuss elliptic, but let's continue. So now parabolic case is when you have b square minus ac equal to 0. Okay. So let's see. So in this case, that would mean that b square equal to ac. That has to be satisfied. Okay. So we need essentially we need zeta eta such that these functions such that b of zeta eta. So here basically I forgot to state it. So in this case the claim is that equation can be reduced to the following form. Which is W theta zeta plus first order derivative is to something like that is the canonical form for parabolic case. Okay, so here only one derivative, one second derivative or second order derivative will appear, which is with only one variable. Okay, so what it means to say is that you will have so basically if this condition is satisfied, that would mean that B and C are 0. Okay, okay. So B and C can be, we can obtain such condition if small b square equal to AC. Okay, so B now if B square is AC, okay, then if I just show that C is 0, then B will automatically be 0, right? So basically what I need to show is that if B square minus AC equal to 0 implies we can find condition such that capital C is 0. Now since I know that B square is A into C, that will, and I know that B square minus AC sign does not change upon coordinate transformation. Okay, so if C is, and I know that B square is equal to AC, then since B square is equal to AC, that would automatically mean B equal to, this would mean that B equal to 0, capital B equal to, so B, because if it is 0 to begin with, it will remain 0 just in the change coordinate system because the sign does not change. So that would mean that B equal, capital B equal to also 0. Okay. So therefore, having just shown that capital C is 0, that will automatically mean B equal to capital B is also 0. And since these are both 0, then basically only a term will survive. Therefore, you will have the form of the governing equation of having only one term with respect to the first variable, taking twice derivative, right? The second order derivative term with respect to one variable. Okay, that was the key term. Okay. Is that all right? So I hope the logic should be clear, right? I will repeat. So what I'm going to say, claim is that if capital C is 0, okay, then I know that since B square minus AC does not change sign upon coordinate transformation, therefore in the changed coordinate system also capital B square will be equal to capital A to capital C. Okay, so therefore now if I have shown if capital C is 0, therefore capital B will also be 0, and if these two are 0, then it automatically ensures the form of the governing equation to have only one second order derivative, okay, which is twice with respect to zeta or the first variable, okay, or one of the variables, and that's it. Okay, is that all right? So this is what. So I have to just show C equal to 0. Now C equal to 0 would happen when. Okay. So C equal to 0 would happen when capital C is equal to 0. That would mean if you just look at the C expression and just use that expression, I think this was your beta y square. Okay, this was the expression for capital C. Let me cross check. So capital C as a function of, there is that expression or not? Yeah, here. So this is capital. Okay, so this I'm directly using and setting it to 0. So this I can write down simply as 1 by A x plus B beta y square equal to 0. So this can be written like this. Okay, so therefore beta must be the solution to the first order variable which is a theta x plus b theta y equal to 0. And we have already seen this, the same form that we saw in the previous class, right? A previous example, you get a first order ODE, right? So this, we all know that this would be basically obtained when dy by dx equal to b by a. Okay, when you have this curve, okay, that would imply theta is constant. Okay, that is what we have already found out earlier, right? So we have already seen this result. Okay. So dy by dx will be constant when if dy by dx is chosen to be equal to b by a, my eta will be constant. Okay, and so basically what we have found here is that as long as we are basically moving on the curve defined by dy by dx equal to by a, where eta is constant, right? C will be 0. Okay, and C will be 0 would mean that I have this expression satisfied. Okay, so basically what we can do is and what is the form of eta? Well, we solve this equation for y versus x. Okay, solve y equals to some function of x plus some constant. Okay, and that will give me constant value to be y minus fx. That is a constant that you can identify with eta as a function of x and y. So that will give me the coordinate transformation required. That will be to y minus fx, where fx is obtained by integrating this thing. Okay, so that is how you obtain this. The same procedure exactly what we followed in the previous example. So once I have found the eta of x comma y, I know that on these when on these set of curves when eta is constant, my equation would appear to have only one second order partial derivative term, okay, which is with respect to only one variable. Okay, so that is the canonical form. Okay, so that is the parabolic equation. Does anyone know an example of parabolic equation? Maybe I can do an example of this. It's a little tedious, but let me do that. Let's do that. So let's do an example. A little tedious, but let's do it. So example, x squared uxx minus 2xy plus y squared. I think I'm doing too much math, so I should not be doing this, but let me just finish this with me. Probably the last bit of detailed math that we can discuss. Maybe a little bit more in optimization part also, because that will also has some mathematics in it. Okay, so this is my equation. Okay, so I have a equal to x squared, b equals to minus xy, c equals to y squared, d equals to x, e equals to y, f and g are equal to 0. Okay, but these are not of any use to us. We are concerned with a, b, and c. Okay, so equation of, so now here, first of all, let's check whether what kind of what kind of equation is that? B square minus AC is x squared y squared minus x squared y squared that is 0. Okay, that means it's parabolic. Okay, and therefore I know that when dy by dx equal to b by a, just in the previous uh, page, we found that parabolic equation, if you have dy by dx equal to b by a, eta will be constant, right? So here I'm doing the same thing, dy by dx equal to b by a, and b is equal to minus xy by a is x squared. That will give me minus y by x. Okay, so that is a very simple form. This can be integrated easily. Dy by minus y equals to dx by x. Okay, that is going to give us actually ln minus ln x plus okay, multiply ln y equals to minus ln x plus some constant. That will give me ln of xy to be equal to constant, okay, or xy is constant. Okay. So I have these set of curves on which I should be able to obtain if I so basically this, if we can identify with eta, okay, then I have eta equals to xy. So along these curves, well, basically when you put xy into equal to constant, that is meaning that you identify eta with xy. Eta as a function of xy has been identified, and along these set of curves, I should be able to reduce this equation to a canonical form where I'll have only u zeta zeta or u eta eta appearing, nothing else. Okay, no other second derivative will appear. U zeta zeta will appear. Okay, so let's try that. Now you note that basically I'm only, so my new transformation rule, my new transformation rule is only for eta. X is not changing, so zeta is the same as x. Okay, so I'm not changing x zeta, I'm only changing x. So for example, I have x and y like this. Okay, so and xy equals to constant would be so you can know xy equals to, these are the curves, right? Xy constant, right? So these curves are forming my theta axis, and x axis is forming my these curves, the grid formed by these set of curves actually now. Okay, x, and so I just imagine that there is no y axis anymore. Okay, so if you imagine that there is no y axis, I'll just erase this y axis, and I have the curves that would look like x-axis and these xy equal to constant curves. This would form my grid. Okay, and along these grids I will be having, if I talk in terms of this current x, zeta and eta, so x is same as zeta, and these are my eta axis. These are my eta lines, right? Constant eta lines. These are my constant x lines. Okay, actually constant x line should be vertical. I think it's still here. Constant x line should be vertical lines and these lines. Correct myself. So these are my constant x line or constant zeta lines. Okay, and these would be my constant eta lines. Okay, constant eta lines would be, well, I'm not drawing it properly, but you get the idea. What are they going to look like? Right? Something like this. Okay, so this kind of grid, on this grid, this equation will transform to a different form, which is much simpler, and will be having only one term, which is this term. Okay, so let's find. So the question is, so basically there are two parts of the question. First part is, what is that coordinate system on which my current equation reduces to the canonical form, and what is that canonical form? Because there are two parts of the problem question. Remember, even in these examples, there were two parts. First of all, what is the particular coordinate system? Meaning, what are the functions zeta and x, zeta of x comma y and eta of x comma y? What are these functions so that the above function, yeah, we assume zeta equal to x, absolutely. That's, I just wrote it here. Okay, because this condition of having c equal to 0 automatically satisfies b equal to 0, and therefore I have only got the condition in eta. There is no need to change x. Okay, only as long as you have only this condition satisfied, you will be having capital C and capital B both 0. Okay, and only a will survive. So therefore there is no need to change zeta. I can only change eta, or I can only define one coordinate system and retain the previous first one. That was the rationale. Okay, so the question is, so that above equation reduces to canonical form, okay, which is having only second order derivative term to be survive, or no other derivative term survive, second order derivative survive. And second question is, what is the what is that canonical equation? Canonical form of the equation. Okay. The first question we have already answered, meaning I have already found eta and zeta as function of x and y. These are my zeta is x and eta is xy. Okay, we already found that particular coordinate transformation. Now the question is, what is on these coordinate system? What is the how does the equation transform to? Okay, to what kind of equation it will transform? Okay, that is a little tedious. So again, because of the fact that you have to substitute for uxx, uyy, uxy, etc. So maybe I can write this as some results which will be useful. So I have, let me rewrite x equal to zeta, y is equal to eta by x. Okay, so if I have to write x as a function of zeta and eta, that will simply eta by zeta. Okay, remember you have two things: eta as a function of x and y, zeta and eta as functions of x and y. And when you invert these, you get x as a function of eta and zeta, y as a function of zeta and eta. Okay, so start. If I have to find zeta x, eta x, etc., you have to write down zeta and eta as function of x and y, etc. Okay, and yeah, I think that should suffice. Okay, well, so all I did was this right hand side is written over here. Okay, this x and y as functions of zeta and eta written over here. Okay, now I also, so therefore I know that zeta x equal to 1, zeta y equal to 0, zeta xx equal to 0, yeah. Zeta xy equals to zeta yx equal to zeta yy, they're all zeros, and for eta x equal to eta was equal to xy, right? So eta x is equal to y, okay, and y is nothing but eta by zeta. Because we have to remember, now we have to switch every term, everywhere where eta x appears, I have to write in terms of eta and zeta, okay, not in x and y. Okay, so and eta y equals to x, okay, which is the same as zeta, okay, and eta xx and eta yy, they are both zeros, and eta xy is equal to 1. Okay, so now so if you just do this, well, I'm going to write this. Maybe x, the original equation, start with the original equation and keep substituting. So x square uxx minus 2xy uxy plus 2yy into y square. Is that the one? Let's check. X square minus 2x y square, x and y. Okay. Okay. So plus x 2x plus y uy. This was your form, right? So now uxx, and I remember uxx had a particular form which was x square, and that read as w zeta 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 x square plus 2w zeta eta. Just copying it down, you can cross check zeta x, okay, plus w eta x square plus w zeta, zeta x. I've given these forms earlier. Please cross check. W eta x. This entire thing is essentially, uxx. Okay, uxx, after you do the transformation, uxx would look like this. Okay. Similarly, uxy minus 2xy, okay, w zeta 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 x zeta y plus w zeta eta zeta x zeta y plus zeta y zeta x plus w that is where it becomes tedious, that's all. Okay. After all this algebra, you get a much simpler form. That is the beauty of this thing. All this effort is worthwhile because in the end you get a much simpler form. That's y square, and then uyy will be, yeah, I have that. Which is 2. Plus. I want you to cross check each term because I may, because I'm also copying down from my previous expression that I gave you. So make sure that these are correct expressions. Plus beta. And let me continue. Plus x ux, we all remember that was simpler form. W zeta zeta x plus w eta x. That was ux. And uy is also a very simple form. W zeta zeta y plus w eta y. Okay, that is 0. So here I have this term as uxy and this term as uyy, okay. And this is ux, this is uy. Okay. All right, and then now we already have obtained these terms, these expressions for eta x, eta y, eta x, eta x, y, etc. Plug these in. So, for example, eta x square is 1. Okay, what are zeros here? Eta x, eta y 0, eta x x. These are all except eta x. All derivatives of zeta x is 1, and zeta y and all other derivatives are zeros. Okay, so therefore I can cancel some of the terms here. Zeta x. Okay, so let's see which terms get cancelled out. Zeta xx gets cancelled out. Eta xx is 0 also, so eta x is cancelled out, and eta x is not cancelling. Okay, that's fine. Okay, so I guess that's it. Eta x. Okay, here I have zeta y cancelling out. This goes to 0, and zeta y, this goes to 0. Okay, and zeta xy goes to 0. Okay, and eta x, eta y, they are not 0, and eta xy is 1, that's also not 0. Eta y is also not 0, zeta x also not 0. These terms cancel out in this one. And here I have zeta y, of course, going to 0. Zeta y here going to 0. And eta y is not 0. Eta yy, zeta yy will of course be 0. Eta yy is also 0. And then here, zeta x is not 0. Eta x is also not 0. Zeta y is 0. Eta y is not 0. Alright, these terms go to 0 each. Okay, so if I just work it out, well, please do that yourself. Okay, so now simplify this entire expression. I'm going to give you the final expression here. Okay. The final expression looks like very simple form, zeta square W zeta zeta plus zeta W zeta W zeta. That is the form we are going to get. Okay. So this is a much simpler canonical form. Please check. This is what you get. Okay, after you substitute all these remaining non-zero terms, you substitute from here. Okay, you substitute from this result. Substitute over here for different terms and simplify. You should get this expression. Okay. So this is so. Please sit down and do it once and convince yourself that is what you're going to get. So this has basically the form of, you can actually assuming that zeta is not zero, that means you're not looking at the center x equal to 0 line. Okay, so if zeta is not zero, then I can divide by zeta square on both sides. Okay, and I will get w zeta zeta plus w zeta by zeta equal to 0. If only one second order derivative term survives. Okay, that is a canonical form of the parabolic equation. Okay, so you have now hyperbolic canonical form, parabolic canonical form, and the last one I'll just elliptic case. I'm not going to again derive everything. So let me just state it. So we had hyperbolic equation, which is b square minus ac is positive. That would, the canonical form is w zeta eta plus first order derivative. First order derivative terms equal to some function of eta and zeta. Okay, that's canonical form. Second is parabolic equation, that is b square minus ac equal to 0. And here I have w zeta zeta plus first order derivative terms equal to some function of zeta and eta. And then I have hyperbolic. So these two I kind of worked out in detail. Here I will not, because there is some complex algebra involved here, and that will take too long for us to discuss. Hyperbolic case, b square minus ac less than 0, then your imaginary quantities coming into picture. I will skip that discussion. All you need to know is the basic idea without getting into details of it. So you have probably you've got some idea of the meaning of canonical forms after discussing hyperbolic and parabolic cases. And for so elliptic case, elliptic, where you have b square minus ac less than 0. You have canonical form is given by simply w zeta zeta plus w eta eta plus, there is no cross term actually, first order derivative term equal to some function of zeta and eta. That will be the generic canonical form. These are canonical forms. And it's always so we'll assume that basically when we are discussing these equations, okay, we'll assume that these have been already reduced to canonical forms. Okay. So we'll start our discussion from the canonical form. Okay. Because remember, solution it becomes easier to handle such solutions, such equations. Okay. So I guess that is it for today. And any question? I'm going to take just 1 hour class today because I have some other engagement. So, any question? If there's no question, then I'll stop the class and we'll resume.